The next thing that I would like to do is spend a little time again talking about current mirrors, because these are very important in practice. So, this is the plain old current mirror. This is M1, this is M2, this is Iref, and let us assume that the overdrive of the transistors is capital delta V, right. Otherwise, we need to keep carrying this VGS minus VT all over the place. So, what is the potential of the drain of M1? We did this before, please. What is it? Yes, backbench. I understand, man. Look at. Yes. Very good. What else? Do you see something written in text below? What is it? What does it say? Yeah. Okay. Now, in terms of known quantity, in terms of these quantities, can you please tell me what the drain potential of M1 is? Well, by the way, what do you understand by gate overdrive voltage? If I denote the gate overdrive voltage by delta V, what is the gate potential? Delta V plus VT. Is this clear? All right. So, now this is the plain old current mirror, and we saw this already. So, if I vary Vx, all right, and if I plot I out as a function of Vx, all right. How does it look like? For what value of Vx will be I out be exactly equal to Iref? It is going to be exactly identical to Vx, identical to Iref if the Vx is exactly equal to Vt plus delta V. So, that point we are going to mark there. What is the slope now of this characteristic I out versus Vx? If I plot if I plot the curve, if I plot I out versus Vx, how will the picture look like? How will it look like? For Vx equal to 0, what is I out? 0, okay. So, what happens as we keep increasing Vx? It will do this, and at certain point it will, and then do that, right. Let me exaggerate a little bit to show the slope, okay. And what is this that knee point there? What is the knee point? The point beyond which it sort of attempts to become flat? Delta. Is this clear? All right. What is the slope now? What is the slope there? Let us assume that the output resistance is, the GM of the transistor is something and RO is something else. So, what is the slope of that? It is 1 by R naught. Okay. So, ideally we wanted it to be what we want ideally is a constant current which is exactly equal to Iref, okay, and we want it to be exactly equal to Iref for all values of Vx, but unfortunately it is not, that is not possible. When Vx becomes sufficiently small, the transistor will go into the linear region, the current has to drop, right. but beyond a minimum voltage we would like that to behave like an ideal current source, correct. So, we see two problems. One is that in this region there is a slope. So, if unless Vx is exactly chosen to be equal to Vt plus delta V, there is not only a slope, but there is also an error in the current that you get out, right. So, for example, if you put a voltage say Vy which is greater than Vt plus delta V, what comment can you make about this current here? Quick. It is of course greater than Iref. How much is it greater than Iref by? It is greater by Vy minus Vt plus delta V by R naught. So, the change in the drain voltage divided by the output resistance will give you the change in the current. Okay. All right. Now, the question is, can we do something to take this bad current source, right, and make it better, correct. Okay. So, we have already seen how to take a bad, I mean when we say bad current source and make it better, what does it mean? What resistance? Huh? Yeah. So, basically we want to increase the output resistance of that current source. Okay. So, the question therefore is, what do we do So, the question is, if we put a box here, okay, all right, what should we do to make this output resistance very, very high? You understand? So, what must be there in this box? What kind of, what must be that box? This must be a current controlled current source. What is the simplest current controlled current source that you know? The common gate amplifier. Okay. So, basically that is the common gate amplifier, and if the common gate amplifier has to work properly, the transistor M3 must operate in which region? When will the common gate work like a current controlled current source? When the transistor operates in saturation, all right. Okay. So, that basically means that this gate voltage Vg must be sufficiently large that M3 operates in saturation. Does it make sense? We will figure out what that Vg is a little later, but let us now plot. So, what comment can you make about the output resistance of, so this is Vx again, this is I out, this is I. So, when Vx is 0, what is the current? It is still 0, all right. Okay. So, now what comment can we make about the, for a given voltage Vy, where all the transistors are operating in saturation, right. Okay. What comment can we make about the slope of the characteristic? If I plot I out versus Vx, you will get another curve like the previous one, right. The question I am asking is, what is the slope of that characteristic? There are two parts, one is the slope, one is the actual value at Vy. They are two different things, right. So, both of these have the same slope, but have different output currents when you put in some V1. So, the first thing that I am going to ask you is what is the slope? To find the slope, what do we do? What exactly are we looking for when we want to find the slope of that characteristic? R out. So, basically we are interested in finding the output resistance there, right, and we have already seen this until we are blue in the face. So, what is the output resistance? What is the output resistance looking in at the point I have drawn in magenta? Okay, what is the output resistance? What is the resistance looking down from the source of M3? R naught. Okay, so what is the output resistance looking in now at the drain of M3? Okay, very good. So, basically please go back and look into your notes, right. We saw that the R out and we discussed this already this morning. The output resistance is nothing but GM R naught times the resistance in the source plus R naught plus RS. Okay, so, basically the output resistance looking in will therefore be GM times R naught. This GMRO is corresponding to which transistor? M3. Okay. So, times RO, that RO corresponds to which transistor? M2 plus RO plus RO, one corresponds to M2 and one corresponds to M3, right, and we know that GMRO is very large. So, this is all approximately equal to GM R naught square. So, the slope of this line therefore is now 1 over R naught times GMR. So, when compared to the plane current mirror, what comment can we make about the slope? Slope has reduced by a factor GM R naught, and since GM R naught is maybe I do not know 30, 25, 30, 40 something like that, basically we see that the output resistance of the current source is increased by an order of magnitude, correct. All right, but another thing, we not only want the output resistance to be very high, we also want the current to be an accurate mirror, correct. Okay. So, the question now is what comment can we make about the output resistance if the output voltage is V, I mean this voltage is Vy. We can see that the slope is now much smaller, right. So, for all practical purposes you can therefore say that this line is almost flat, right, when compared to the previous line, right. So, this is pretty much flat. So, now the question is what, I mean two questions that arise. The first is, what are the two questions that arise? We know the slope of that line, what else do we need to know about that line? The actual current that is flowing, correct. So, can we get a quick estimate of what the actual current that is flowing is? Or okay, let me now or let me make this easier. What Vg must I use so that the current at the output is exactly equal to Iref? Okay, what comment can we make about the current of M2 versus that of M3? And that is the same as the output current, correct. Okay. Now, if we want the current in M2 to be exactly identical to Iref, what comment can we make about this potential? If the current in M2 has to be exactly identical to, the current in M2 has to be exactly identical to Iref, what comment can we make about the drain potential of M3? It should be Vt plus delta V. Okay, so this is Vt plus delta V. So what comment can you make about Vg? What is the M3 is identical to M2. So what comment can you make about its gate source voltage? M3 is identical to M2. M3 operates in saturation. M2 operates in saturation. The gate source voltage of M2 is Vt plus delta V. What comment can we make about the gate source voltage of M3? Which is what? Which is Vt plus delta V. The gate source voltage of M3 and M2 will be, approximately the same, because their drain source voltages need not be the same, but to first order they are approximately the same. So what comment can we make about Vg therefore? If we want I out to be exactly equal to I ref, Vg must be 2 Vt plus 2 delta V. Okay. All right. Now, what is the minimum voltage that is needed? Remember, all this nice stuff only works when all the transistors are in saturation. So, what is the minimum Vx needed to make sure that all the transistors operate in saturation? So, basically remember that if you have an NMOS transistor, the transistor will be in saturation, the edge of the triode region is defined by when the drain goes one threshold below the gate. So, basically now we have the gate potential is 2 Vt plus 2 delta V. So, the minimum voltage therefore needed will be Vt plus 2 delta V. So, we have after this we have a constant current, right, but below this it will do something like this. Okay. Is this clear? So, so what is the moral of the story? When you compare these two current sources, what do we see? So, we can compare the two current sources with 3 parameters, right? What are the 3 points of interest? The slope, the accuracy, and the minimum voltage that you need to be across the current source for it to behave like one, correct? So, so basic mirror, and this mirror which is a where you take a basic mirror and where you basically put a common gate amplifier atop M2, right. This is what is called a cascoded current mirror. Okay. Now, of course, the way it's so now that we want 2 Vt plus 2 delta V, I mean, can somebody suggest a simple way of generating 2 Vt plus 2 delta V? Is the gate source voltage when a transistor has a current, is diode connected, and you pump in IRF through it. Okay. Now, I want, okay, so I have a 1 volt battery, I want to get 2 volt battery, what do I do? Yeah, if I had an amplifier with which could amplify 1 volt and give you 2 volts, its supply voltage must be higher, right. So, one easy way of doing it is to say, basically, if if I want 3 volts, I have a 1.5 volt battery, I will put 2 in series, correct. Okay. Now, based on this discussion, can you tell me, I have Vt plus delta V, I want 2 Vt plus 2 delta V. So, what do you think I can do? You can put Okay, so where am I going to put the two transistors in series? On the right side of M3. Okay, well, okay, good. Let us see if, so the suggestion is the following. Let us see if where this leads us. So, we need 2 Vt plus 2 delta V. So, the suggestion, two transistors in series, and what should I do to the drains and gate of those two transistors? This is M1, this is one transistor, then connect that gate is connected, gate of M1 is already connected to, add a same mirror, okay, both gates meaning which one? Very good. Okay, so basically the idea is the following, we need Vt plus 2 delta V there. So, we have Vt plus delta V. So, in principle what will we do if we had a battery which was Vt plus delta V what do we do now? What is this potential? What is that potential? 2 Vt plus 2 delta V. So, what should we do now? To connect that point to the gate of M3. So, we can do that, correct, which is equivalent. And how do I now realize this battery now? Copy M1 and paste it. Okay, and I just turn M3 around. Okay. All right. So, this is basically 2 Vt plus 2 delta V. Okay, this is Vt plus delta. Okay, so let's so this is the cascode mirror. Okay, so the minimum voltage needed, output resistance, and accuracy. All right. So, the basic mirror accuracy is not great. All right. And what is the output resistance? Okay. All right. What is the minimum voltage? Okay. Now, complete the second row. Look at the picture again. Open your eyes. Is what? Vt plus 2 delta V. Okay. Output resistance? So, it is RO times GMRO, and is much better, provided, and that is because the gate, remember that this accuracy will only show up when the gate of M3 is biased properly at 2 Vt plus 2 delta V. All right. Okay. Now, so what is so when we move to the basic mirror and the cascode mirror, what is it that we gain and what is it that we lose? The accuracy is improved, the output resistance is improved, but the minimum voltage has gone, you know, up, right. So, for example, let us say VDD is 1.2 volts, which is a very common supply to use these days. Let us say delta V is 150 millivolts and VT is half a volt, right. So, the minimum voltage for the basic mirror is what? 150 millivolts, whereas for the basic cascode mirror, what do we see? VT plus 2 delta V, which is basically 800 millivolts, right. So, you can see that the a big fraction of the power supply voltage is lost. Okay. So, you can have that current source only operate from 800 millivolts to 1.2 volts, only 0.4 volts of headroom is left for that current source. Okay. So, ideally what would we like to do? What is the problem with the, so what is the problem with the basic mirror that the cascode mirror solved? Output resistance was very low and right, but then what is the problem? That we fixed those two problems, but now we inherited a new problem. A new problem is that the minimum voltage needed is higher, correct. So, what do you think we can do? So, let us go back to our all right. So, let us now try to see if we can solve the minimum voltage problem. All right. So, the reason why we had the minimum voltage problem was that both the transistors have to be in saturation. Now, let us see, of course, now this ensures that both the transistors are in saturation, but what is the potential at the drain of M2? What is the potential at the drain of M2? Vt plus delta V. So, is this it is, of course, M2 is definitely in saturation, but is it deep in saturation or is it just at the edge of saturation? M2. What do you understand by deep in saturation? Yeah, okay. So, so in other words, how much extra headroom does M2 have, right, with respect to the edge of the saturation region? If M2 had to be, I mean, the drain source voltage needed for M2 to be in saturation is just delta V. But what is the VDS? It actually has, it has Vt plus delta V. So, that Vt is simply, you know, extra voltage, right, okay, which serves no purpose as far as, the saturation region is concerned, correct. Okay. But because the drain of M2 had to be at Vt plus delta V, the gate of M3 has to be at 2 Vt plus 2 delta V, right, and consequently the minimum Vx needed becomes Vt plus 2 delta V. Is that clear? I mean, the reason why the minimum voltage is this large value of Vt plus 2 delta V is that the drain voltage of M2 is too high, therefore, the gate voltage of M3 has to be Vt plus delta V higher than that, which then basically means that Vx has to be a minimum voltage of Vt plus 2 delta V. Okay. So, if we want the minimum voltage to drop, what comment can we make? How do we do this? No, think commonsensically, right? Why? What is the root cause? Why is the minimum voltage at the drain of M3 so high? Because the gate of M3 is very high. Why is the gate of M3 very high? Because the drain of M2 is very high. Correct? Alright. So, now if you want to reduce the minimum voltage, what comment can you make about Vg? Should we increase it or should we reduce it? You should reduce it, right? So, what is the lowest Vg we can use before M2 goes into the triode region, or when M2 is just at the edge of saturation? Oh, what is this potential? If the gate voltage of M3 is Vg, what comment can we make about it? Source potential. Vg at the gate is known of M3, let us say it is Vg. I am asking you what the drain potential of M2 is. It is simply Vg minus the gate source voltage of M3, and what is the gate source voltage of M3? It is minus Vt minus, okay. So, if you want to ensure that M2 is in saturation, what comment can we make? Okay, we will stop here. I think I am already overshot. We will continue tomorrow.